I want you to do something for a second. Just take a look around your immediate environment right now.
And I'm actually doing it too.
Right, like I've got this glass of water sitting in front of me. There's a heavy metal spoon resting on a wooden coaster here. I'm breathing in the air of this room. And, well, I'm looking right at the flesh of my own hand.
Exactly.
When you actually stop and observe it all, the sheer variety of material in the world is almost overwhelming. All of those things look completely different, they feel completely different, and they behave in, entirely distinct ways.
It really is. And that observation right there, that's the perfect entry point into our source material for today's deep dive.
Awesome.
Because when you look at that incredible diversity, the water, the metal, the wood, the air, the biological tissue, it hides one of the most profound paradoxes in physics and chemistry.
Which is?
That all of that endless variety is built from the exact same severely limited set of ingredients.
Right.
I mean, we are talking about roughly 100 naturally occurring elements from the periodic table.
Okay, let's unpack this, because that is a wild concept.
Yeah.
If we define an atom as, like, the absolute basic building block of our material world, the smallest indivisible unit you can break an element down into, we have a serious math problem.
We really do, yeah.
It's like looking at a standard bucket of Lego bricks. You've got your red 2x4s, your yellow 1x2s, maybe 100 different shapes in total. We have to somehow get an infinite number of complex, entirely different, squishy, hard, liquid, and gaseous macroscopic objects out of that limited box of parts.
And the answer doesn't actually lie in the atoms themselves.
Wait, it doesn't?
No, I mean, it's not about the individual Lego brick. The secret to the entire material world is chemical bonding.
Oh.
It's about the very specific mechanisms those atoms use to stick to one another. So our mission for this deep dive is to take this incredible source material on chemical bonds and use it as a shortcut.
Right. A way to make sense of it all.
Exactly. We want to translate that invisible microscopic world into a framework that makes everyday life suddenly, make perfect mechanical sense.
So we have to start with the fundamental driver then. To understand how atoms build literally everything, we have to look at the thermodynamics of why they join together at all.
Yeah, the why is crucial.
Because they don't just drift around completely separately, existing as these aloof single ingredients floating through the vacuum. They actively seek each other out. And that comes down to energy.
It always comes down to energy.
The universe fundamentally favors lower energy states. It's fundamentally lazy, I guess you could say. It wants stability.
That's a great way to put it. And this raises an important point about atomic anatomy. Right in the middle of an atom, you have a very dense, positively charged core called the nucleus.
Okay.
And swarming around that central core, you have a cloud of much lighter, negatively charged particles.
The electrons.
Right, the electrons. But those electrons aren't just a random swarm. They exist in specific layers or shells. And the only ones that really matter for our conversation today are the ones in the very outermost layer.
The valence electrons.
Exactly, the valence electrons. The driving force of all chemistry is that atoms possess an inherent thermodynamic restlessness unless that outermost shell is perfectly full and structurally tidy.
So atoms are basically like someone trying to find the perfect sleeping position.
Ah, yeah, exactly like that.
Like they are restless, tossing and turning, inherently unstable on their own, and they can only get perfectly comfortable, meaning they can only achieve that low-energy, stable state by interacting with the pillows, or in this case, the atoms right next to them.
That is spot on. They are continuously trying to minimize their energy, since the vast majority of atoms in the universe do not naturally possess a full, tidy outer shell. They just can't achieve that stable, lower energy state in isolation.
They have to mingle.
They are forced to negotiate with their neighbors. They reach that comfortable state by rearranging those valence electrons. So depending on who they bump into, they might share those outer electrons, hand them over entirely, or, pool them together into a massive collective.
So bonding is simply atoms rearranging their outer electron clouds to reach a lower energy state.
That's it. As the source material points out, every physical property you see around you is just a byproduct of that pursuit of stability.
Okay, so let's get into the actual mechanics of those negotiations. The source breaks this down into distinct strategies driven by a concept called electronegativity.
Right.
Electronegativity is essentially just a measure of how greedily an atom wants to hoard electrons, right?
Pretty much, yeah.
So if you have two atoms bumping into each other with wildly different levels of greed, you get an intense electrostatic negotiation resulting in our first major category, the ionic bond.
And that disparity in greed is the key part. You have one atom that requires relatively little energy to just eject an electron and empty its outer shell.
Because it wants to be stable.
Exactly. It has low ionization energy. Then you have a neighboring atom with a massive appetite for electrons, high electron affinity.
So it's a perfect match.
It really is. The energy trade-off makes perfect sense for them. The atom with low ionization energy completely ejects its electron, and the greedy atom captures it.
But this transfer creates a massive physical consequence, doesn't it? I mean, an atom is normally electrically neutral. The positive protons in its core perfectly balance the negative electrons in its cloud.
Right, usually.
If an atom ejects a negatively charged electron, the math changes. It now has more positive protons than negative electrons, turning the entire atom into a positively charged ion.
Ication, yeah.
And the atom that took the electron becomes a negatively charged ion, an anion.
Yeah.
Now you have a positive entity and a negative entity sitting right next to each other.
And we all know what happens with opposite electrical charges.
They attract.
Strongly. They attract each other with immense force. That intense locking electrostatic attraction is the ionic bond. And they don't just lock together in isolated pairs either.
Oh, they don't?
No, if you have a bunch of these ions, they organize into a vast alternating three-dimensional grid. Positive, negative, positive, negative.
Oh. Like a lattice.
Exactly. That rigid, highly ordered grid is a crystal lattice.
So a classic everyday example of this crystal lattice is ordinary table salt, right? Sodium chloride.
Yep, perfect example.
The sodium atom ejects an electron, the chlorine atom eagerly captures it, and they lock into that alternating 3D grid, which is why if you look closely at salt, it naturally forms those hard, sharp little cubic crystals.
That's exactly why.
But wait, I have to challenge this premise for a second. If this electrostatic attraction is so immensely powerful, locking these atoms into a rigid crystalline grid, why does salt dissolve the second you drop it in a glass of tap water?
That is a great question.
Right. It seems entirely contradictory for a bond that strong to just yield instantly to room temperature water.
It does seem like a contradiction until you look at the unique geometry of water molecules. Water acts like a dense swarm of tiny magnets.
Tiny magnets?
Yeah, we refer to water as a highly polar solvent. When you drop that hard salt crystal into the water molecules essentially gang up on the crystal lattice.
Oh, wow.
Because of their own slight electrical charges, they are highly effective at orienting themselves around the charged sodium and chlorine ions, prying them apart one by one.
So they just rip the grid apart.
Basically, the water molecules form what we call a salvation shell around the individual atoms. They isolate them and functionally shield them from feeling that strong attraction to each other. Dissolving is simply the crystal being dismantled and quarantined atom by atom.
So the ionic bond is incredibly strong in a dry vacuum, but water is overwhelmingly good at infiltrating the lattice and breaking up the electrostatic relationship.
Exactly.
Here's where it gets really interesting. You and I are mostly made of water. Human blood, muscle tissue, the sap in trees, water is everywhere in biology.
It is everywhere.
If ionic bonding only produces rigid crystals that are easily dismantled by water, biology cannot rely on giving and taking to build complex structures. We need permanent, robust molecular architecture that survives in a wet environment.
Which is why what's fascinating here is that the universe provides a completely different strategy for those situations.
Okay, what is it?
Giving and taking is too extreme and too vulnerable to polar solvents like water. To build the complex architecture of life, atoms rely on a strategy where the electronegativity, the greed for electrons, is relatively balanced between the interacting atoms.
So nobody wins the tug of war.
Right. Neither is willing to give up an electron entirely, so they are forced to compromise through sharing.
Ah, so we are talking about covalent bonding.
Yes.
Instead of a transfer, two atoms approach each other and their outer electron clouds actually physically overlap, right?
Yeah.
Hold a pair of electrons in common, and those shared electrons inhabit a new space that basically glues the two nuclei together.
They merge their probabilities, yeah. This shared electron density is the covalent bond. Our source refers to covalent bonding as the workhorse of the living world.
I love that phrase.
It's accurate. Because these bonds are highly directional and incredibly strong, they allow atoms to build discrete, complex molecules rather than just, endless repeating grids.
Covalent literally translates to holding the valence electrons together. This is the bond underlying almost everything complex. Like the water we just talked about dismantling the salt, it's a covalent molecule. two hydrogen atoms firmly sharing electrons with one oxygen atom.
Exactly.
And the atmospheric gases we breathe are covalent. The elaborate macromolecules of life, our DNA, our folded proteins, the complex carbohydrates we consume, they're all intricate architectures held together by shared covalent bonds.
And if we look closely at biological molecules, carbon emerges as the undisputed champion of the covalent world.
Oh, carbon is amazing.
It's uniquely optimized to form stable, complex, shared bonds with up to 4 other atoms simultaneously. This allows it to act as, like, a molecular junction box, branching out to build the immense varied backbones required for the complexity of living organisms.
But carbon doesn't just build the squishy components of biology. Our source highlights a staggering demonstration of how the geometry of covalent bonds dictates physical reality.
Oh, the diamond example, yes.
Right. If you take pure carbon atoms and arrange them so every single atom shares robust covalent bonds with 4 other carbon atoms in a continuous tetrahedral three-dimensional lattice,
Yeah.
you get a diamond.
Which is incredibly hard.
It is the hardest naturally occurring material on the planet, entirely because of that unbroken 3D web of shared electron density.
That tetrahedral web is structurally impenetrable. But you can take those exact same carbon atoms and arrange them so they form covalent bonds in flat hexagonal sheets.
And what happens then?
In this arrangement, the strong bonds only exist along a 2-dimensional plane with very little holding the individual sheets to one another.
You get graphite,
Exactly.
the soft gray material inside a pencil that rubs off onto paper. I mean, the tip of my pencil and the diamond on a drill bit are literally the exact same elemental building blocks.
It's crazy to think about.
The profound difference in their physical properties, one easily flaking apart, the other capable of cutting solid rock, has nothing to do with the atoms themselves. It is entirely dictated by the structural geometry of how they chose to share their electrons.
It perfectly illustrates a core theme of material science. Macroscopic properties are emergent. They are not hidden inside the atom itself. They emerge from the structural relationships between the atoms.
Okay, so we have the rigid electrostatic grids of ionic bonds, and we have the highly directional, localized sharing of covalent bonds building up water, biological tissue, and diamonds.
Right.
But what about the metal spoon resting on my coaster here? Metals don't fit either of those models, do they?
No, they really don't.
They aren't brittle, alternating crystal lattices, and they aren't discrete individual molecules sharing specific electrons.
Which brings us to a third major strategy, which the source describes as a radical departure from the other two. It operates on a principle of communal pooling, known as metallic bonding.
Communal pooling.
Yeah. In a chunk of metal, the atoms have very low electronegativity. They hold onto their outermost electrons very loosely. Instead of handing an electron over to a specific partner or sharing it in a localized bond, billions of metal atoms collectively release their valence electrons into a shared delocalized space.
A communal sea of electrons.
That's the visual.
It's a quantum mechanical phenomenon where the valence shells of all the atoms overlap across the entire macroscopic object. The electrons are completely untethered from any individual nucleus.
You end up with a structure where positively charged metal atom cores are suspended in this highly fluid roaming sea of negative electron density. The collective electrostatic attraction between all the positive cores and the permeating negative sea is what binds the entire chunk of metal together into a solid object.
And what's brilliant about this specific physical structure is that it effortlessly explains the defining behaviors of metals that we interact with every single day.
Conductivity.
Yes. Take electrical conductivity. Electricity is quite simply the directional flow of charged particles. If you hook a battery up to a diamond, nothing happens, because all the electrons are locked tightly in localized covalent bonds.
They're stuck.
But a lump of metal is essentially a pre-existing reservoir of highly mobile, delocalized electrons. You introduce an electric voltage to one side, and that communal sea instantly shifts, flowing current right out the other side.
The atomic structure directly provides the mechanism for the macroscopic behavior. It also explains malleability.
Oh, right, being able to bend it.
Exactly. A blacksmith can heat a piece of iron and hammer it into a thin sheet, or a manufacturer can stretch copper into a thin wire without the material shattering. If you strike a rigid ionic salt crystal with a hammer, you force the precisely alternating positive and negative ions out of alignment.
And then they repel each other.
Right. Positive aligns with positive, negative aligns with negative. The electrostatic repulsion spikes, and the crystal just shatters into powder.
So a salt crystal is like a rigid line dance. Everyone is perfectly spaced out. If someone shoves you, you collide with the person next to you, the formation collapses, and the dance is basically over.
That's a great analogy.
But a metal is totally different. The sea of electrons makes it more like a crowded mosh pit or like a packed dance floor. People can slide smoothly past one another. They can be pushed and shoved into entirely new formations. But the music, which is the pervasive electron sea, keeps the whole group moving together as one unified entity without anything snapping.
Exactly. The bonds don't snap when stressed. The atoms simply slide past each other, and the fluid sea of electrons immediately flows around them to maintain the structural integrity.
That's incredible.
The fluidity of the delocalized electrons provides the malleability and ductility of the solid metal. The electrons act as a flexible glue. So we've explored the three powerful internal strategies atoms use to build structures: the electrostatic negotiations of ionic bonds, the highly specific sharing of covalent bonds, and the communal pooling of metallic bonds.
So what does this all mean for how these structures interact with each other in the real world? Like, if a water molecule is perfectly comfortable, having achieved its low-energy state through stable covalent bonds, holding the hydrogen and oxygen together, why does it interact with the other water molecules in my glass?
Why don't they just float away?
Yeah. Why don't the complete molecules just ignore each other like inert little spheres?
Well, if we connect this to the bigger picture, we have to look beyond the internal construction of molecules. We have to introduce the fourth layer our source emphasizes: intermolecular forces.
Okay, what are those?
These are the much gentler, weaker attractions operating between separate, fully formed molecules.
So they aren't building the molecule itself, they're dictating how the molecule behaves socially with its neighbors.
Precisely. While these forces are vastly weaker than covalent or ionic bonds, they are absolutely crucial to macroscopic reality. They rely on the concept of dipole moments.
Dipole moments.
Yeah, so even in a neutral covalent molecule like water, the electron density is rarely shared perfectly equally. The oxygen atom is highly electronegative. It's an electron hog.
It pulls the blanket towards itself.
Ha, exactly. It pulls the shared negatively charged electrons closer to itself. This leaves the oxygen side of the water molecule with a slight negative charge, and the hydrogen side exposed with a slight positive charge.
The molecule essentially becomes a tiny, weak magnet. It has poles.
Right. And the slightly positive end of one water molecule is gently drawn to the slightly negative end of a neighboring water molecule. It's not a full electron transfer or a deep orbital overlap. It's just a transient, noticeable attraction.
Just a little tug.
Exactly. This phenomenon, specifically called hydrogen bonding in water, is just one type of intermolecular force. These forces govern everyday physical properties like viscosity, surface tension, and why some materials feel sticky while others feel slippery.
A fantastic example from the source material here is the grip of a gecko's foot.
Oh, I love that one.
It's so cool. A gecko can walk upside down on completely smooth, solid glass. They aren't using suction cups or chemical adhesives. Their footpads are covered in millions of microscopic hairs that leverage these incredibly weak intermolecular attractions, specifically van der Waals forces.
Yeah, and individually, the attraction between a molecule in the hair and a molecule in the glass is negligible.
Basically zero.
But you sum up millions of those tiny dipole interactions, and you generate enough gripping force to hold the entire weight of the animal against gravity.
That's wild. And these weak forces are also responsible for the phases of matter under normal conditions, right?
Absolutely.
Going back to our water example. If water molecules did not possess those dipole moments, if they didn't have those weak intermolecular forces gently clinging them to one another, the thermal energy at room temperature would cause them to simply fly apart.
Water would be a gas.
We wouldn't have liquid oceans. We wouldn't have liquid blood flowing through our veins. The fundamental environment required for biology just wouldn't exist. So, what does this all mean for how we categorize these? If covalent bonds are the permanent marriage holding a molecule together internally, are these weak attractions basically the casual social glue that determines how molecules mingle with their neighbors?
That is exactly what they are. The physical behavior of matter is a story told simultaneously on two scales. The powerful internal bonds build the discrete molecular characters, and the subtle intermolecular forces dictate the complex social dynamics of how those characters interact to weave the fabric of our everyday environment.
We really need to take a step back and synthesize what all of this means, because it drastically recontextualizes human experience. I mean, the only reason I am sitting here feeling the solidity of a wooden table, drinking liquid water, and existing as a highly structured biological machine, the reason you, the listener, exist as a complex physical being rather than a formless, chaotic soup of isolated atoms, is simply that atoms are not content to be alone.
It all traces back to that microscopic drive for a lower energy state.
Right.
Driven strictly by the physical pursuit of a full outer shell of electrons, atoms reach out. They organize using just a few reliable strategies. They transfer, they share, they pool into Cs, and they gently cling. From that relentless, tiny impulse, the immense complexity of the material universe rapidly assembles itself.
The crystalline structure of salt, the bendable conductivity of metal, the vast liquid ocean, the impenetrable diamond, and the tissue of your own body. Everything solid, liquid, and lasting around you is ultimately just trillions of atoms holding hands in very specific geometric patterns, trying to find a stable thermodynamic arrangement.
Understanding these mechanisms transforms how you perceive your environment, doesn't it?
It totally does.
You aren't just observing inert objects, you are witnessing countless trillions of ongoing quantum negotiations and electrostatic attractions, all operating continuously in the background to maintain the physical shape of your reality.
Before we wrap up this deep dive, there is one final provocative thought I want to leave you with, building on everything we just talked about. We have spent this time exploring how the incredible variety of our world, from DNA to drill bits to copper wiring, is entirely emergent from just these three main types of atomic bonding occurring under standard Earthbound conditions.
But standard conditions are just a tiny fraction of what exists in the universe.
Exactly what I'm thinking. What happens to these strict rules of chemical bonding when we force atoms together in extreme environments? Think about the crushing, unimaginable pressures at the core of a gas giant like Jupiter,
Oh, man.
or the ultra-high energy environments generated inside experimental particle physics laboratories. Under physics-breaking pressures and temperatures, do the concepts of ionization energy and orbital overlap simply break down?
It's a huge question.
Right. Could those extreme environments force atoms to share or pool or fuse their electron clouds in entirely unprecedented ways? Are there bizarre states of matter and entirely undiscovered classifications of chemical bonds waiting to be found at the extremes of the cosmos that we haven't even dreamed of yet?
It is a profound frontier for material science and physics. If the simple pursuit of a stable electron shell can engineer the sheer complexity of life on Earth, the structures forged in the high-pressure depths of the universe might defy our current understanding of chemistry entirely.
So, next time you look around your room, remember the restless atoms successfully stabilizing your world, and just wonder what completely alien architectures they might be building out there in the dark.